Hello everyone. In this lecture we will discuss polarization. So to understand the polarization we can divide the material into two categories. One is conductor and second is dielectrics. So first point here is conductors. So in conductors, electrons move freely through the material. It means that many of the electrons are not associated with the particular molecule or one or two electrons per atoms are free. Now here in case of dielectrics, all electrons are attached to specific atom or molecules, and they are tightly bound. And second point here is they can move a bit within the atom or molecule. Okay. Next we will discuss induced dipoles. Now here in case of induced dipoles we will discuss what happened to a neutral atom when it is placed in an electric field. Okay, that is what happened to a neutral atom when it is placed in an electric field. Now here suppose we have a atom that is suppose this is a nucleus and here we have electrons. So this is the case when electric field is equals to 0. Okay, so when we apply the electric field, that is then there is a separation of positive and negative charges. That is, when electric field is not equals to 0, then the positive charge, that is nucleus, will try to move along the direction of electric field, and the negative charge will move in the opposite direction. So as a result, what we get induced dipoles. So this is nothing, this is a induced dipole. Now in continuation of this, if the field is large, that is electric field is large enough, it can eject the electron or ionize it, and as a result dielectric material become conductor. Okay, and if the field is less, then positive mean nucleus, and negative charges attract one another, and this hold the atom together. This holds the atom together. Okay, so what is a induced dipole? That is, when we apply the electric field, then the positive charge will move towards the electric field and negative charge will move in the opposite direction, and as a result we get induced dipole. So next point here is, so as we discussed, here we have a induced dipole. Suppose we represent this induced dipole with the help of a P. Then here the direction of the induced dipole is same as that of electric field, or mathematically we can write P, that is induced dipole, is directly proportional to the electric field. Okay, or we can write P is equals to alpha E. So here alpha is a proportionality constant and is known as a atomic polarizability. So here alpha is known as atomic polarizability. Further, this atomic polarizability, it depends on the detailed structure of the atom. So this atomic polarizability alpha depends on the detailed structure of atom which is under consideration. So this is the case when we have a neutral atom. Now here, when we have molecules, so this is the neutral atom and we have a simple case. Now when we have a molecule, then the situation is quite not so simple. That is, for molecules, suppose we have a simple case of a molecule, that is carbon dioxide. So in this case, suppose here we have a carbon, here this is a oxygen, and also here we have a oxygen. Okay, so now here when we apply the electric field, then we have two components. One is parallel to the electric field and second is the perpendicular to the electric field. So in case of a parallel, the atomic polarizability is equals to 4.5 into 10 raised to power minus 40 coulomb square meter by Newton. Okay, and in case of perpendicular, alpha is equals to 2 into 10 raised to power minus 40 coulomb square meter over Newton. Okay, so it means in this CO2 we have a two component of atomic polarizability. One is for parallel case and second for the perpendicular case. Okay, or mathematically we can write P is equals to alpha perpendicular E perpendicular plus alpha parallel or E parallel. Okay, now again this is a simple example of a molecule, because here CO2, in case of CO2, all the atoms are arranged in a straight line. Now in continuation of this, for completely asymmetrical molecule, again alpha is P is directly proportional to E, or we can write Px equals to alpha xx Ex plus alpha xy Ey plus alpha xz Ez. Similarly, for Py, this is equals to alpha yx Ex plus alpha YY EY plus alpha YZ EZ, and finally PZ is equals to alpha ZX EX plus alpha ZY EY plus alpha ZZ EZ. So here we are 9 constants for atomic polarizability for the molecules. That is here 1, 2, 3 and 4, 5, 6, 4, 5, 6, 7, 8 and 9. So we have 9 constants for the atomic polarizability to explain the molecule. So till now we discussed the induced dipoles. Now next we will discuss alignment of polar molecules. That is, in this case we already have dipoles, permanent dipole moments. Okay, so we already have permanent dipole moments, and we are interested to align these dipoles in the direction of the electric field. Suppose we have a case water. In case of water, what we have, suppose this is a oxygen, here we have hydrogen, H positive, this is a O negative. Similarly here we have H positive. Okay, and here these are the dipoles, and we know this angle is 105 degree. Okay, so this is the direction of P, that is polarization. So now, so these are the molecule we already have dipole moments. Okay, next we will discuss what happens when polar molecules are placed in electric field. What happens when polar molecules are placed in electric field? Now here, suppose we have a polar molecule, that is, here we have one positive charge and here we have one negative charge, and in the presence of electric field, here we have a F positive, that is force, and here we have a F negative, and the distance between these two, suppose this is D. Okay, so now here F positive, this is equals to QE, and F negative is equals to minus QE. Okay, so if the field is uniform for uniform field, F positive is equals to F negative. Okay, and the torque will be, that is, N equals to R plus cross F plus R negative cross F negative. So R positive is nothing, this is a half the d by 2, that is, this is equals to d by 2, F positive is equals to QE, okay, plus minus d by 2 for R negative, and here we have a minus Q by QE, okay, and total value is equals to QD cross E. Okay, so total is equals to QD cross E. Further, this QD is equals to P, that is dipole moment. So here what we discussed, N is equals to QD cross E. Okay, D is a vector quantity, but this QD is equals to P, that is dipole moment. So finally N, that is torque, is equals to P cross E. So this is a torque when we have a uniform field. So now for non-uniform field, F positive is not equals to F negative, that is force due to positive charge is not equals to force due to negative charge. Okay, so if this is the case, then the net force, that is F is equals to F positive minus F negative. Okay, or we can write Q E positive minus E negative, and here we have very small difference, so we can write force is equals to Q delta E. So when we have a non-uniform field, the net force is equals to Q delta E, and in case of a uniform field, net force is equals to 0. And here net torque, this is equals to N, that is P cross E, that is due to uniform field, plus due to non-uniform field, that is R cross F. So here R is nothing, this is a dipole length. Okay, so here torque is responsible to align the dipoles in the direction of electric field. So now here we will summarize the lecture. That is, first point, when we have a neutral atom or we have non-polar molecules, then in that case, when we apply the electric field, then there is a separation of positive and negative charges, that is electrons and nucleus, and as a result we get the induced dipoles or induced dipole moments. And in second case, when we have polar molecules, that is we already have dipoles, that is we already have dipoles. For example, suppose we have, this is a polar molecule, then they already have dipoles or permanent dipoles. So this is the case when electric field is equals to 0, that is in the absence of the electric field. So net dipole moment is equals to 0 because dipoles are randomly oriented. But when we apply the electric field, that is when electric field is not equals to 0, in that case the dipoles will try to orient in the direction of electric field depending upon the strength of the electric field. Okay, so here 100% alignment is not possible because the temperature of the material also contribute here, and temperature of material also matter. At high temperature, the alignment of dipoles definitely is poor as compared to at low temperature of the material. So finally, mathematically we can write polarization, that is P is equals to dipole moment per unit volume. Dipole moment per unit volume, that is P, we represent capital P, we represent with this polarization. Small p is the dipole moment over volume. Okay, thank you.